Okay guys, so today we're going to be talking about entropy and mutual information. So before we do that, just to kind of give a one sentence summary of what we did in the past couple of weeks. Neural encoding and decoding both focused on what does the response of the neuron tell us about a stimulus. So today we're going to go a bit further and consider how much does the neural response tell us about a stimulus. And the first way we'll do that is through entropy, which is a measure of how interesting a set of responses are. So just to give a quick example, let's say each response was the exact same, the neuron fired in a very predictable manner, let's say every 5 seconds, right? Then the entropy would be very low because there's no surprise factor, there's nothing interesting about the results. On the other hand, if it almost seemed random, then the entropy would be very high, right? As in this second response right here, because there's no pattern that we can discern. So this is where we build upon what we learned about previously. So remember the spike count firing rate was the number of times the neuron fired divided by the time. And initially this is what we'll use to come up with the idea of entropy because it's the simplest one. So P of R in the second bullet, that's basically the probability of observing a response with a spike count rate of R. So let's say R was 5 times per second, right? Then P of 5 would be the probability of getting 5 times per second. Because remember, each time that the neuron fires, it could be a different spike count firing rate. So H of P of R, which is not entropy, it's kind of like an intermediary function. I'll call it the surprise function. Right, so we want it to have two basic properties. First, it has to be decreasing, because if you think about it, let's say P of R was really high, right? Then we want H to be low, because a low probability is more surprising, but a high probability is less surprising. So, and that's one property. And the second property is we want it to be linear. So basically, if we have two independent firing rates, R1 and R2, we want to be able to add the two surprise factors. And this is just convenient, as you'll see in a second. So we want a function that is decreasing and has this linearity property. And so it turns out we can use the negative log function. And we use base 2 because we wanted to know, like, did it fire or not. It's useful in binary situations. But technically you could use any other base if you wanted. Sometimes you'll see the natural log used. But this function is not entropy, remember, it's just the surprise factor. So entropy would be if we weight this measure over all the possible responses, right? And the reason we weight it is to get a balance. So that way a very high probability doesn't contribute too much, and a super high surprise factor doesn't contribute too much. So for example, let's say the probability of response was very high, right? So if P of R is very high, well, then the negative log of P of R, which is the surprise factor, will be very low. So, and vice versa for the super high surprise factor. If one is high, the other will be low. So that's why no term really dominates the entropy. So consider these two scenarios. One is kind of like the trivial scenario. So let's say that it fires with a constant R every single time, right? So let's say 5 times per second, or whatever the units are, right? Well, then the entropy will be 0, because P of R will be 1, okay? But then the surprise factor, which is the negative log, base 2 of P of R, negative log of 1, that'll be 0. And as you can see, we multiply them because we're weighting it by the probability of getting that firing rate, right? So that way, 0 times 1, we get 0. So the entropy is 0, which is expected because there's nothing interesting about the result at all. Consider the second scenario where the neuron fires with 2 rates. I'll denote them positive and negative because there's just 2 rates and it's just a binary situation. Positive and negative don't actually mean anything regarding signs, right? So the probability of getting a positive response plus the probability of getting a negative response has to be 1 because there's only 2 responses. So plugging that in, we find this expression right here. And then if we graph this, we get this kind of parabolic looking function. And this makes sense because the entropy would be maximized at 0.5, right? Because that way it's almost random which firing rate we get. So that this graph makes intuitive sense. Now we move on to mutual information. So entropy tells us how interesting results are, but it doesn't tell us why the variation occurs. And so the neuron provides info about a stimulus only when its variability is correlated with change in the stimulus. So in other words, if the if the variability has nothing to do with the stimulus change, if the neuron's just firing randomly, then it doesn't provide us any info about the stimulus, right? So it only provides info about the stimulus when its response is because of the stimulus. So what we can do is we can compare responses obtained by using different stimuli on every trial, and then compare that with responses obtained by using the same stimulus on every trial. And we can kind of subtract the difference, as you'll see in a second. And this is the essence of mutual information, which is how much of the response is due to the stimulus. So remember, we want to take the total entropy minus the entropy that's that from trials that involve the same stimulus. So we want to kind of subtract out the contribution and variability not due to the stimulus change. I like to call this like the background noise, right? So we want to subtract out the background noise. So then we take the entropy of responses given the stimulus, and this is what we'll use to just derive the noise entropy. So basically it's the same thing as normal. So remember that the standard version of entropy was this. And then the log is, again, the surprise factor. So all we're doing is we're replacing P of R with P of R given S. That's what this bar means, right? And we care about the response given the stimulus because that's what we're going to subtract out. And now we weight this by the probability of the stimuli. So again, no factor has, I guess you would say, too much weight. And that's why we add this term right here. And again, so this H noise right here is the entropy associated with the part of the response that's not due to the stimulus change, right? It's the background noise. And this is because we weight by this P of S factor. That's why it's not due to the stimulus change, because we're weighting by how much the stimulus change is. So at the end, we get this mutual information formula. We take our total entropy right here, and we subtract out the noise entropy. And this becomes a plus sign because, as you can see here, this is negative. So since we're subtracting, so we get this expression. So before I'm going to do some derivations, I just want to talk quickly about conditional probability and partitions. So you might have learned before in research stats or somewhere else that if you have two events, that the probability of getting both is, let's say probability of A and B is equal to the probability of A times the probability of B given A, or that's equal to the probability of B times the probability of A given B. And you might have seen something like, for independent events, probability of A and B would be probability of A times probability of B. And this is the most common one, but it's only true if they're independent, right? This one is the more general form that always works. This is always true. And the reason is because if they're independent events, then over here, the probability of B given A, well, that's just the probability of B, because given A doesn't change anything about B since they're independent events. So we get this right here. And to explain it a little more visually in a Venn diagram, I'll explain it using this Venn diagram right here. So the probability of A given A and B, which you know is this intersection right here, is the probability of A, so the total probability right here, times the probability of B given A. So times the probability of B given that A is already true. So that's right here. Right? So then we'll get the probability of A and B. And now talking a little bit about partitions. You might have heard this before. First I'll start with an example and then I'll go to the more general definition. So let's say we had a system of car accidents, right? Let's say that the probability that someone between 16 and 20 crashes the car is 0.5, that the probability of someone between 20 and 25 crashes the car is 0.3, the probability that someone 25 and older, let's say, is 0.2, right? Because they all have to add up to 1. Then I'll say that, well, let's see. Then we'll say that the cost of insurance for someone 16 to 20, that it's between 13. Actually, ignore this example. I think it might confuse a little bit. So I'll start with the more general definition first, actually. So, okay, this is like the formal definition. If B1 to Bn form a partition of the sample space, blah, 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 and you get the summation here. But I don't think this really sheds light immediately, so that's why I'll go on to the Venn diagram first. So let's say we had A, this space here, right? You'd obviously know that the probability of A is just this area of whatever this circle is, right? That's pretty simple. But I can also, let's say I form a partition of the whole space. You might have heard this entire rectangle called the universe, right? Let's say I partition that. So we have a couple of events that make up this universe. We have B1, we have B2, all the way up to Bn, right? So that way, well, what's another way we can describe P of A? We can add up all of these intersections. So this blue area right here, this blue area right here, this blue area right here, and this blue area right here, and all these, right? We can add those up and get P of A. But what is each one of these blue areas? Well, it's just the intersection of B1 and P of A, right? And you might think, why is this useful? And I'll explain this in a second. But if we intersect each of these areas, so let's hear what we're doing, right? We're saying P of A is the sum of P of A and P of 1, plus P of A and P of 2, plus P of A and B of 3, right? We keep summing those up, and we learned in the previous, like in the conditional probability, that we can replace this expression with this one. So at the end of the day, we're just adding up these little partitions to get the total sum. And the reason we do this is because when we, going back to this mutual information stuff, remember we had this already. You can look back on the previous slide if you don't remember. But we can substitute P of R with this expression right here. And we're summing over S because we're taking the probabilities with respect to S. And the reason we do that is because because this summation is in terms of S and R, whereas this one is just in terms of R. So by doing this summation over S, they both become with respect to R and S. So this summation right here, this one on the left becomes, I'll just write it here again. Okay, this is what it becomes. And then moving to this step, again, these are a common factor. Using some log properties, you can find that, if you subtract two logs, you can actually divide them on the inside. And then you get this expression for mutual information. And then we do one more step with this. We know that P of S times P of R given S is just P of R, and then this comma means and. P of R and S, and then substituting this right here for P of R given S with P of R comma S divided by S. So this expression and this expression are equivalent, right? So then we get this expression, and and you might be wondering, okay, why did we go through all the trouble just to simplify a little bit? It might help in calculation, but otherwise, what's the use? Well, if you look at this expression, it's symmetric, which means that I can switch R and S and nothing would change, right? Because P of R and S, this is the same. This is the same if I switch them. And the bottom, it's the same if I switch them, right? So that means that when we expand the expression again, for mutual information, the expression is the same as if we just switched all the R's and all the S's. So if you look back at the original expression, every place you see an S, there will be an R and vice versa. Which means that the stimulus variability due to the response change, well, that's the same as the response variability due to the stimulus change, which is something that might be intuitive, but it's nice to see that mathematically it also makes sense because of the symmetric expressions, right? And that's a powerful tool. So let's consider two scenarios again. So the first scenario, called the trivial scenario, is that the response and stimulus are totally independent, that the response has nothing to do with the stimulus, that neither predict each other. Okay? So that way the probability of response given the stimulus is the same as the probability of response, right? They have nothing to do with each other. So if you plug that into mutual information, either expression here, because this also means that the probability of stimulus given response is equal to probability of stimulus, right? Because they're independent. So if you plug this into the previous expression here, this one right here, then you will get 0, which makes sense because none of the response is due to the stimulus change, and none of the stimulus change is due to the response. In other words, they're just doing their own thing. Now let's take scenario 2, that the stimulus completely determines the response, so that the probability of a rate of a certain stimulus, I'll call R sub S, is equal to the probability of the stimulus, right? So stimulus determines the response completely, and therefore vice versa. If you plug that in, you get this expression right here, right? But since P of S is equal to P of R sub S, you plug this in, and you will get this expression right here, and this is just the total entropy. We didn't have to subtract out any background noise because there was no background noise, because the stimulus determined the response completely. There was no variation naturally in the response, right? So that gives us the total entropy. Now we have a third scenario, which is the most interesting scenario. Let's say we have two responses, again, binary responses, right? And the probability of getting a wrong response, which I'll call P sub x, is the probability of, let's say we actually had positive, let's say we got a positive response, but the result was actually negative. So P of R positive given that the result was negative. We'll call that the same as the probability of getting a negative response given that it was actually positive. We'll call that the error rate, P sub x, right? And here we assume, because these are equal, that the probability of getting a positive response and the probability of getting a negative response are both 1/2. So the reason we do 1/2 versus like 1 is because I want the total entropy to add up to 1 here, to make the graph a little bit easier to interpret. Technically, these probabilities, they should be between 0 and 1, but if you go over, like mathematically, the result won't change. It'll just be a scalar factor. But for like practicality, you should keep it between 0 and 1. So plugging this into mutual information, we get this long expression, which doesn't matter as much. But if you look at the graph, then we get this decreasing function, right? This is, like, if you think about it, you can pause the video and think. So if you look at, if the error rate is 0, then the mutual information is 1 bit, right? Because there is no background noise. The error is 0. There will never be any variation not due to the stimulus. All of the variation will be due to the stimulus. On the other hand, if the error rate is 1/2, well, then we're just flipping coins. This has nothing to do with the stimulus. The response is basically completely random. That's why we have no mutual information. The mutual information ends up to be 0. Right? So at the end, like, to sum up kind of, this lecture today focused on entropy and mutual information. And before we focused on what does the response tell us about a stimulus, today we focused on how much does it tell us, right? And later we might discuss some probability tools that are used and statistics tools that are used to analyze this more deeply, because here we just consider like one or two or three scenarios. But sometimes you'll use probability distributions like the exponential distribution to kind of probabilistically gauge what the response is given the stimulus, and the other way around as well. So with that, if you need, we'll be posting this lecture on in the description below, and feel free to ask us any questions.